Hello everybody and thanks for attending in this talk. The title of this talk is Acoustic Communication and Networking. This presentation covers the issues we face with an underwater acoustic communications and proposes different methods to overcome these challenges. The outline of this presentation is shown here. First, we mention a few characteristics of underwater channel, and based on them we propose an efficient acoustic communication algorithm. Next, since cognitive communication is of importance for us, we talk a little bit about spectrum sensing. Then we list a few challenges that exist in underwater acoustic networking and propose a near optimum algorithm for underwater broadcasting. We will briefly talk about the acoustic modems, and finally we conclude the talk and mention some future work. The underwater acoustic channel is one of the most challenging wireless communication media known to man. The sound propagation speed is very low in comparison with the speed of light, and this causes long propagation delays when we want to transmit a signal from one node to another. The environment is not uniform, and the transmitted signal may experience different sound speed as it travels through long distances. The ambient noise and the attenuation depend on the frequency of transmission. In high frequency, there is very high signal attenuation, but lower ambient noise, and vice versa. This causes frequency and distance dependent bandwidth, as it is shown in the figure for different distances. According to the experiments we had for the underwater channel, we noticed that the time delay of channel tap varies with time as shown in the figure. This causes time and frequency spreading. This kind of channel is known as multi-scale multi-lag channel. It means that the amplitude and the arrival time of the signal on each path varies with time. The spread in time and frequency domain generates intersymbol and intercarrier interferences in the received signal. Still, we can see that the delay spread of the channel is very large, around 40 milliseconds, but the frequency spread is quite low, around 4 Hz. In order to overcome the interferences, we propose to transmit the signal into several small subbands. The benefit of this design can be listed here. First, with a narrower bandwidth, the existing channel estimation equalization method can be applied. Second, with a narrower bandwidth, the number of effective channel taps in the discrete domain can be kept low. In the figure, we show the structure of the transmitted signal. For the proposed transmitter in the previous slide, we have designed a multi-branch receiver. Each branch is designed for one pass of the channel. The receiver is like a rate receiver but more complicated. Before applying the match filter, we first down-convert the received signal. Then we sample each branch in a way that the effect of varying channel tap is removed. After that, we insert the equalizer for each branch. The equalizer coefficients can be obtained either from decision on each branch or all the branches. This is our contribution for the receiver. We use a combination of the information from all the equalizers and construct the coefficient for the equalizers iteratively. For this receiver we have used turbo coding. That's why the iterative approach would help us to build the equalizer's coefficients more effectively. The performance of the designed receiver has been shown in these figures. In figure A and B, we showed how using turbo coding with iterative self-decision decoding would help us to decrease the amount of error. For instance, after 20 sweeps or iteration, we can see that the performance has been improved greatly. In figure C, we did not combine the information from all branches, but we only used the information from each branches for their equalizers. It can be seen that the performance is not as well as using the joint the combination of all information. As shown in figure D, the performance of the traditional approaches, which do not consider the effect of varying channel taps on the signal, are the worst among all these approaches. In a cognitive communication system, we require to estimate the wideband spectrum of the signals which are active in the environment. Then we can find free subbands and transmit our desired signal in those subbands. We have worked on this issue a little bit, and we propose an energy efficient and time delay considering approach to scan the whole environment. The details of this work have been provided in the deliverable. In order to avoid or reduce collisions in underwater acoustic wireless sensor network, we have to employ a medium access control to share the resources orthogonally or efficiently among the nodes. These methods can be divided into two categories: deterministic, such as TDMA, SDMA, or random, such as Aloha or Mach. Most of these protocols are currently used in terrestrial wireless sensor networks. However, the unique characteristics of underwater acoustics, such as low propagation speed, high transmit energy, small channel capacity, make these protocols inefficient. Next, we will see how we can overcome one of these challenges, for instance, long propagation delay in our proposed MAC protocol. If we use TDMA approach, which is very common in current underwater systems as a MAC protocol, we have to add a guard band to each packet to avoid the collision. The amount of guard band is the maximum range divided by the sound speed. This amount is around 1 second for only 1.5 kilometers of transmission, which is really large in comparison with packet length, which is around 50 to 200 milliseconds. However, with the knowledge of the positions of the nodes, we can schedule the transmissions and add the guard bands adaptively in a way that avoids collision and reduces the total time of transmission for broadcasting. We have formulated this problem and proposed an efficient algorithm for that. The details of the algorithm is explained in the report. Here we focus on its performance. From the figure, it can be shown that the required time for performing a task for the proposed algorithm, represented by the red curve, is much smaller than the traditional approaches, which are shown in its blue curve. In order to implement our proposed algorithms, we need a programmable acoustic modem that satisfies the requirements of the Noptolus project. For example, operating frequency, bit rates, and so on. We could not find this kind of programmable modem, but we proposed a partially programmable one. The block diagram of this approach is shown here at the bottom figure. The analog part of this approach is fixed, but we can attach our laptop computer to this modem and build a fully programmable digital part. This is our approach for different experiments that we can have in the future. In this talk, we briefly overview the tasks we have done about acoustic communications. We propose an efficient communications algorithm, a method for spectrum sensing, and a MAC protocol for packet transmission. In the future, we focus on more comprehensive tests and optimizing the parameters of the proposed algorithms. And finally, I thank you for your attention.